Here's a problem that might look innocent at first. We need to find integer values for m and n that satisfy this logarithmic equation. The different bases here seem to make things messy, but there's actually a really beautiful structure hiding underneath. Our first task is to convert all logarithms to a common base. This will reveal the hidden structure. Let's start with our original equation. Notice the logarithm base 9 on the right side. We need to convert this to base 3 using the change of base formula. The change of base formula states that the logarithm of b to base a equals the logarithm of b to any base c, divided by the logarithm of a to base c. This allows us to convert between different logarithm bases. Applying the change of base formula, logarithm base 9 of 6 equals logarithm base 3 of 6, divided by logarithm base 3 of 9. Now, logarithm base 3 of 9 is simple. Since 3 squared equals 9, this logarithm equals 2. So we simplify the denominator to 2. Next, we'll simplify the right side by multiplying through. Substituting back into our original equation, 10 times logarithm base 9 of 6 equals 10 times the quantity. Logarithm base 3 of 6 over 2. We can simplify by dividing 10 by 2. This gives us 5 times logarithm base 3 of 6. Now we'll expand logarithm base 3 of 6 using logarithm properties. First, we recognize that 6 equals 2 times 3. Using the product rule for logarithms, the logarithm of a product equals the sum of the logarithms. The product rule states that the logarithm of x times y equals the logarithm of x plus the logarithm of y. This is one of the fundamental properties of logarithms. So logarithm base 3 of 6 equals logarithm base 3 of 2 plus logarithm base 3 of 3. Logarithm base 3 of 3 equals 1. Since 3 to the first power equals 3, we simplify to get logarithm base 3 of 2 plus 1. Let's substitute this result back into our equation. Our equation now reads m minus n times logarithm base 3 of 2 equals 5 times logarithm base 3 of 6. We substitute our expanded form for logarithm base 3 of 6. This gives us m minus n logarithm base 3 of 2 equals 5 times the quantity logarithm base 3 of 2 plus 1. Now we distribute the 5 across both terms inside the parentheses. We get m minus n logarithm base 3 of 2 equals 5 logarithm base 3 of 2 plus 5. The key insight is that we can match coefficients on both sides. Since logarithm base 3 of 2 is irrational, the coefficients of this term must be equal, and the constant terms must be equal. Looking at our equation, we can separate it into two parts. The constant terms are m on the left and 5 on the right. These must be equal. Therefore, m equals 5. For the logarithm terms, negative n times logarithm base 3 of 2 must equal 5 times logarithm base 3 of 2. This gives us negative n logarithm base 3 of 2 equals 5 logarithm base 3 of 2. We can divide both sides by logarithm base 3 of 2, since it's non-zero. We obtain negative n equals 5. To isolate n, we multiply both sides by negative 1. Therefore, n equals negative 5. Let's present our final answer. m equals 5 and n equals negative 5. Let's verify our solution by substituting back into the original equation. Here's our original equation. Substituting m equals 5 and n equals negative 5. Simplifying the left side to 5 plus 5 logarithm base 3 of 2. And we showed that 10 logarithm base 9 of 6 equals 5 logarithm base 3 of 6. Using our expansion, the right side becomes 5 times the quantity logarithm base 3 of 2 plus 1. Distributing gives 5 logarithm base 3 of 2 plus 5. Both sides are identical. Our solution is verified. Thanks for watching. If you found this solution helpful, please like this video and subscribe for more math content. See you in the next one.